All right, we're about to start the last chapter of this first of a calculus series. Chapter 5 deals with integrals. What integrals deal with, we learned in the first 12, 13 weeks, derivatives. Which was called differential calculus. This deals with rate of change, the slope of a curve at a given point. Now, this last part, this chapter 5 and calculus 2, deals with something called integral calculus, which finds area under a curve and volumes. We're going to look at three specific types of examples here. The first one, we're going to look at area under a curve. The second one is going to be the distance an object travels. And the last one is going to be the average value of a function. We're going to see how integrals will play a big role in that. So let's begin. The first one, areas. What's the formula for area? Two-dimension calculations. Area is base times width. I mean, this should have been easy. It's been calculus. This has been algebra 1. Should have been pre-algebra, actually. That's what an area is. We're going to be using area, the area calculation, because if we're looking at areas, how do we find, what do we need to find the area? We need to have a formula. The formula is this basic formula here. So let's first begin by looking at the function on the closed interval 0, 2. What's this graph going to look like? Work out some points if you don't know. Plug in some points. Remember, we're between 0 and 2, so plug in some points. What is the function at 0? At 0, the function is 2. What is it at 1? It's also 2. What is it at 2? It's a horizontal line. There's nothing tricky about it. May not be difficult to you. But again, you have to know these basic concepts of algebra. If not, then before taking calculus 2, I would take algebra over again. Or pre-calculus over again. Because you have to know this inside and out. So what is the area of f of x on this interval? So we're looking for this area here, inside this box. So the area formula is base times width. What's the base? The base is 2. It goes from here to here. What's in this case, it's height. What is the height? It's from here to here. So the area is 4 squared units. Let's see how else we can get that. What if we take that same picture, the same function, what if we cut it into 2 pieces? We're still looking for the same area, but now we have the area of this one, and we have the area of this one. So the total area is the area of the first one plus the area of the second one. What is the area of the first one? The base is 1. The height is 2. What's the area of the second one? The base is 1. It's 1 unit from here to here. And the height is 2. So it's 2 plus 2 equals 4. The same thing. Same concept. Now let's take it into 4 rectangles. So we have the area of this one, this one, this one, and that one. So the total area is the sum of all these smaller areas. So what is A1? The base is how far? 1/2. The height is 2. A2, what's the width? 1/2. What's the height? Then A3, it's 1/2. It's also 2. And then A4 is 1/2 and also 2. So simplify these. The 2's cancel, so we get 1. The 2's cancel, so we get 1. The 2's cancel, we get 1. So the area is 1 plus 1 plus 1. So the area is 4. Same thing. And we keep on going. We can make these intervals a lot smaller. It's easy because we have a constant function, but not all functions are that simple. What if our function was 1 minus x squared on the interval 0, 1? What does that graph look like? Go back to algebra. What kind of function is it? It's quadratic. What does a quadratic look like? What's a curve? Yeah, it's a curve. That's quadratic. But since there's a negative in front of it, it's flipped across the y-axis. Now we have a translation, a vertical translation of 1. So at 0, the value is 1. At 1, remember our intervals are 0 to 1. So I have 1 minus 1 squared. 1 minus 1 equals 0. So this one is here. Since it's a curve, it has a bend. Find the area under the curve, f of x, on the closed interval 0, 1. So we do it the same way. If you took the area automatically, if you took the area here, what's the base? And what's the height? So we're saying that the area is going to be 1. Is that right or wrong? Why?
Because it's look like curve. So and the base with the height, it's like a shape. It's like
Right.
a square.
Is it going to be, is this too high or too low? Right, because what this says is the base is 1, the height is 1. So what this is defining is the area of that cube. So we have a lot of extra space right here wasted. Right, it's too high. So how do we fix that? Let's do what we just did. Let's cut this in half. Now we have another problem. Since it is a curve, we have 2 ways of looking at it. It's called we can look at inscribed and circumscribed. Inscribed means inside. Circumscribed means outside. And what these are going to eventually give us, will eventually give us Well, this will give us what's called a lower sum and an upper sum, where the lower sum will be less than the upper sum. But now since we're cutting it up, but are these actual values? Are these the true values of the area? No. So what we're going to be looking for we know our area will be between our upper and lower sum. So let's look at the first one. One way we can look at this remember, we need rectangles. So we're going to use our base is a half. This is a half. This is a half. But the heights are different. So the area, since this is on the outside, this is the upper. Because it's on the outside. Our base is 1/2. What is our height? How high is this box? Right. Well, we see it that we see from the graph, because now since we're dealing with the upper half, we go with the higher bound with the 0. If we put 0 in the original function, we get 1. That's this first part. That's A1. This is A1 plus A2. So what's A2 going to be? The base is 1/2. But what's the height? No, it's not. It can't be 1. There's only one that is the beginning. Everything after that is lower than 1. How do you find it? The height is our f of x. Remember, the height is the y value. So what is it when x is 1/2? 1 minus 1/2 squared. So 1 minus 1/4 is 3/4. So 1/2 times 1 is 1/2. 3 times 1 is 3. 2 times 4 is 8. So now we get a common denominator. We get multiply by 4. So it's 4/8 plus 3/8 is 7/8. That's the area of the upper bound. Seven divided by 8 is 0.875. Okay, so now let's look at the lower bound. This is the upper bound because it's from the outside, because now we have a whole bunch of this area that's wasted. Let's look at the lower bound. We're cutting it into two pieces. Now the area of the lower bound for the lower bound, we're not gonna have enough. We're missing this area. So it's gonna be less than the exact area. And so we use the endpoint. So we use the endpoint. What's the area gonna be here? Again, for this one, since we want the area that's less than the curve, so we use this point. That's our first one. So we have 1/2 and f of 1/2. That's this first area. Then we have to do the same thing with the other one. So we have the base is 1/2. And the height is f at 1. Because we use this value. We'll work it out. So we have 1 minus 1/2 squared plus 1/2, 1 minus 1 squared. One minus 1/4, 1/2 times 0. So 1/2 times 3/4 is 3/8. So this is the lower sum. Remember, the true area under this curve is between your lower sum and your upper sum. So it's between 0.375 and 0.875. Can we make it a better estimation? If we can make these two numbers closer, if we can make these two numbers, the AL and AU, if we can make those closer, then we get a better estimation. We keep on getting closer to it, then we get to the true answer of the area under the curve. So what we're going to do now instead of 1/2, we're going to take 1/4. There's 1/4, 2/4, 3/4. I'm gonna do them both on one. So you see what we're gonna do here? We're gonna cut it into more pieces. Remember what we want the lower bound on the left and the upper bound on the right. This is the lower bound or the lower sum. This is the upper sum. So for the lower sum, are we going to be inside or outside the function? Is it inscribed or circumscribed? Which one gives you a bigger answer, inside or outside? The bigger answer goes on the outside. So for the lower, we want the AL on this side. We want the upper on that side. How do we find the lower bound? Well, we take these points, and from there, we create our rectangles. So now the base is 1/4. Notice all of these bases are all 1/4. So that part has to be remain the same because we have to have the same size rectangles. So now this first one, since we're using this value here, we use that. So we take the x as 1/4. Then the next one is 1/4 base, and the f function is at 1/2 because I'm going to take this height. Then 1/4 times 3 f of 3/4. And then 1/4 f of 1. Because you notice I'm taking it on the right-hand side. So now we have to find these calculations. What is f of 1/4? What is our function f? So this is 1 minus 1/4 squared. The next one is 1 minus 1/2 squared. 1/4, 1 minus 3/4 squared. And then 1/4, 1 minus 1 squared. Instead of bobbleheading, instead of just copying what I'm writing, I want you to try to do something in your seats. Because I ask you basic algebra questions and you're having trouble time answering those. Please try this. Practice what you know. I'll let you guys finish, work on this one first, and then I'll unpause it. 1/4 squared is 1/16. 1/2 squared is 1/4. 3/4 squared is 9/16. 1 squared is 1. 1/4. 1 minus 16 is 15/16. 1 minus 1/4 is 3/4. 1 minus 9/16 is 7/16. 1 minus 1 is 0. So that gives us our area. It's much easier if we have all of them being 16th on the denominator. So I can make this one into 12/16. So it's going to give us the same denominators. So now we have 1 times 15 is 15. 4 times 16 is 64. 1 times 12 is 12. 4 times 16 is 64. 7 times 1 is 7/64 plus 0. And 15 plus 12 plus 7. 27 plus 7 is 34/64. I need a decimal of that. So, well, yeah, this should give me a decimal of that. This equals 0.53125. So that's the lower area. And we got to do the same thing. One fourth. I'll keep it all as 2/4, 3/4, and that's 1. Now we're looking for the upper sum. So for the upper sum, we have to be on the outside of the graph. So we use the lower bound. So we make this rectangle. We make this rectangle. We make that rectangle. And we make that rectangle. Because we want our rectangles to be outside the graph. So the upper, the reason it's upper because it's the greater value. Area 1, area 2, area 3, area 4. So So the area, the base is 1/2. And the height is 1 minus 0 squared. Plus, not 1/2, it's 1/4. 1/4. Notice, it's very important. What x's are you putting in this first one? Since it's on the outside, we use the 0. And for the next one, we're using this one, 1/4. Then for this one, to make this rectangle, we use the 2/4. The next one we have 1 minus 1/4 squared. Then the third one, we have 1 minus 3/4 squared. And then 1/4 is 1/0. We have 1/4. We have, nope, that's 2/4. I'm sorry, it's 2/4. Then we have 3/4. So 1 minus 0 squared is 1 minus 0. 1 minus 1/4 squared is 1/16. 1 minus 2/4 is 4/16. 1/4, 1 minus 3/4 squared is 9/16. Again, don't bobblehead. Learn, you should know algebra. This is basic math here. So the first one is 1 minus 0 is 1. 1 minus 1/16. So 16/16 minus 1 is 15/16. 1/4. 1 minus 4/16 is 12/16. 1 minus 9/16 is 7/16. I hope everybody knows where I'm getting these numbers from. 1 minus 9/16. 1 minus 9/16 is the same as 16/16 minus 9/16, which is 7/16. One times 1/4 is 1/4. 15 times 1 is 15 over 64. 12 over 64. 7/64. So 1 is the same thing as 16/16. So it's 16/64 in the first one. We have 16 plus 15 plus 12 plus 7. 31/43. So what's that gonna equal? This equals 0.7812. All right, so let's look at the last two we did. When n is 2, the number of divisions, our bounds were 0.375 and 0.875. Then when we broke it down to 4 segments, point 0.51, 0.53125, and 0.7812. What was 125? 0.78125. So what do we notice here? What's that?
Area of the rover.
Is always less than upper, it has to be. Yes, that's but-
I mean, very close
when.
when and is same feature.
Yes. So the more divisions we make, the closer. So let's look at what how far these guys are apart. So for the first one, we have 0.875 minus 0.375. That difference is 0.5. The next one we have 0.78125 minus 0.53125. So yeah, so the difference, exactly, good observation. That's exactly the observation. The more divisions we make, more separations we make, the closer these numbers will get, the closer we get to the actual area. So that's what, so if we had n equals 10, n equals 100, n equals 1,000, n equals 1,000,000, these numbers will get closer and closer and closer and closer and closer together. Eventually, after we do enough of those, then we get the same answer. And that's the true area of the curve, which is what we're looking for here. But there's a third method, because this is pretty ridiculous if we have to go higher and low and all this sort of stuff. Can we estimate the actual one? Is there a better way? There's a third way. Well, let me show you. These are all the same function. And let's say we did 1/4, 2/4, 3/4. 1/4, 2/4, 3/4. Unfortunately. All right. We did the outer two. For the lower sum, the lower area, we took it from the right-hand side. And we found these areas. No, that's down there. There's no area there. Then for the upper, we took it on the larger point. So for the lower sum, we didn't have enough. We're missing that area. We're missing that area. For the upper sum, we have too much. How can we get something in the middle of those two? Is there a better way? This is what they were faced with when they first developed this process. Newton, Leibniz, and a guy named Riemann fixed it. Well, if this one's too little and this one's too much, what would Goldilocks say? What's in the middle? That's just right. So what Goldilocks would say is, let's take the midpoint and then go from there. So my graph would be, it would look like this. So let's say this is 1/4. This is exploded. So if this is my midpoint, thank you. So if this is my midpoint, then I have a little below and a little above. So this is below, and this part is above. What's going to happen there is with these, we wasted all this area. We had too much area, but this way, this area that's not enough and this may too much, they'll eventually wash out. So our X values, since our division is in 1/4, what's half of 1/4? 1/8. So C is 1/8. It's half of our interval. And we're gonna do that to each one of ours. We're gonna take the midpoints of them. So we have to figure out what we have to do is we have to find the midpoints of each of these intervals. And then from there, that is going to be our height. So our areas will be the same 1/4, but now it's the midpoint. So this is 1/8. What's the midpoint between 1/4 and 2/4? So we take these two, add them together. 1/4 plus 2/4 is 3/4 and divide by 2.
Mm.
So it becomes 3/8. If you look at it, it goes 1/8, 2/8, 3/8, 4/8. This is going to be 5/8, 6/8, 7/8, and that's 8/8. So our areas are going to be 1/4, 1 minus 1/8 squared. 1/4, that's 1 minus 3/8 squared. 1/4, 1 minus 5/8 squared. 1/4, 1 minus 7/8 squared. Because remember, our function itself was 1 minus x squared. We're using these x's. We get 1/4, 1 minus 1/64, because 8 squared is 64. 1/4, 1 minus 9/64. 1/4, 1 minus 25/64. 1/4, 1 minus 49/64. One minus 1/64 is 63/64. One minus 9/64 is 55/64. One minus 25/64 is 39/64. And then 1 minus 49/64 is 15/64. So we got 63/256. 55/256. 39/256. And 15/256. 3 plus 55 plus 39 plus 15. $172/256. And the area is 0.6718. And if you look at that, this area, which we just calculated using the midpoint, is always inside the bounds that we've gotten, the upper and lower bounds of our previous examples. So even though this one's not exact, it's a close approximation, the closest we can get. Why is that? The reason being because the midpoint method so this is our 0, this is our 1/8, and this is our 1/4. If we use the lower bound, we have that big area there. All that's wasted. If we use the lower bound, all that's missed. But if we use the midpoint method, this area, which is not enough, and this one's too much, they cancel each other out. So the midpoint method makes it a lot closer. The more intervals you have, that means the smaller these things get together, the more accurate your answer becomes. So that's the concept that we're doing in this chapter. Let's look at distance traveled. Remember, distance traveled deals with time and position. And velocity was what? The first derivative of our position function. But if we're given the velocity, how can we say anything about the position of our car, of our vehicle, our moving object? So what we have to do is we have to figure out a way to determine, since that's the first derivative, what is our position? What we have to figure out is a way of determining this function. Because if we took the derivative of this, then the velocity is the first derivative. True. The constant goes away. So we have to try to figure out this out. So if we have a moving object from point A to point B, then our position is the difference, or our distance traveled is our difference between our functions. This tells us how far we traveled. Remember the example we had of the rock exploding and going straight up? Let's look at how far that rock traveled. In one of these chapters, we had a rock that an explosion, and a rock was sent up, and it came back down. So I want to know, how far did that rock travel? How far defines distance? What's the formula for distance? The rate of the object times time, how long it traveled. That's the formula for distance. So what we're looking at is something here. From A to B. If we break this up in different time intervals, the distance covered here in that, since it's broken up into these segments, each of these are called delta t. We break it down to each interval of time. So each one of these are delta t. They're the same distance, or same unit of measure. This happens in t seconds. So then what would distance be? Distance is a function of time. Rate is the same thing as speed. The rate is how far something travels over, how far it traveled over a unit of period of time, which is velocity. And since each of our times are the same, we multiply it by delta t. So what we're going to have here is we're going to have the velocity at time 1 times delta t plus the velocity at time 2 delta t, the velocity at time 3, and so on and so forth. The velocity at time 4 delta t, and the velocity at time 5, how far we go to. Looks familiar? Same thing we did for the area for the curve. Was for the area of the curve, we dealt with the base times the height. The base was our delta x. And the height was f of x. Now, whether we use the lower end or the upper end or the midpoint, that's what these formulas tell us. So it's the same type of formula. It's going to be f of x1 times delta x, f of x2 times delta x, and so on and so forth. So you see, it has the same concept, same procedures. So we're not changing anything. We're just changing the application of it. Okay, so here's our example. The velocity function of a projectile fired straight up into the air is given by f of t, because it's time, 160 minus 9.8 meters per second. Because we have to have our function that defines the movement of our object. It says use the summation technique just described estimate how far the projectile rises during the first 3 seconds. How close do the sums come to the exact value of 435.9 meters? All right, that's a lot of writing, a lot of reading. Now we got to put it together. So what do we know? We have to use this function. We know it's fired straight up. And we're looking at how far the projectile rises. First 3 seconds. Let's draw a picture here real quick. So at time 1, time 2, at time 3. So this one, the first time is at 0. It begins. This is the seconds. 1, 2, 3. We're looking at time. Why do we need to know time? Because what is our delta t? So remember, our formula said we have to have delta t. Oops, that's what I forgot t here. 9.8. Okay, here, why do we have 9.8 here? And why is it negative? But what makes it go down? What makes it a parabola? Gravity. 9.8 is meters per second in gravity. It's negative because the force is always acting down. 160 represents the initial velocity of the object. That's what it start at rest. It doesn't go anywhere, but at its velocity at once it explodes is 160 meters per second. So we have this. Now find f of t at t equals 0, 1, 2, and 3. So the distance traveled equals f of t times delta t. Distance. Oh, this is a subscript. So the first one is at t1 delta t. Then we have f of t2 at delta t, f of t3 at delta times delta t, and then f of t4 at delta t. What's t1? T1 is 0. What's delta t? 1. Delta t is t2 minus t1. Then f of t2 is f of 1, delta t, which is 1, plus f of t3, which is 2, times 1, plus f of t3, which is 3, times delta t. Remember, our function was 160 minus 9.8 t meters per second. So we have 160 minus 9.8 times 0 times 1 plus 160 minus 9.8 times 1 times 1 plus 160 minus 9.8 times 2 times 1 plus 160 9.8 times 3 Actually, no, I only have 3 intervals. 1, 2, 3 intervals. I don't need this last one. So I only have 3 intervals. At 0, from 0 to 1, 1 to 2, and 2 to 3. So we have 160 minus 0 times 1. 160 minus 9.8 times 1. And 160 minus 9.8 times 2. 16 is 19.6. And so 160 minus 0 is 160. 160 minus 9.8 is 150.2. 160 minus 19.6 is 140.4. Add up these, we have 160.0, 150.2, 140.4. 6, 0, 15. It's 450.6. So that is our distance traveled. What's our units? Yeah, so it's distance is meters. What was B asking? So for the first 3 seconds, it traveled 450.6 meters. How close to the sums come to the exact value of 435.9? So how do we find that? Okay, hold it. Let's look at this. Like our first example, we had the lower bound and an upper bound. This is the lower bound because we go from the lower numbers. Because we haven't really used this number. So what if we go from these, from 3 to 2, that's delta t is still 1. From 2 to 1, delta t is still 1. And then from 1 to 0. Let's see what that gives us. Are they going to give us different values? So from here to here, that's delta t. From here to here, that's delta t. And from here to here, which is equal to 1. We're going to do the same thing again. So we have rate times time. So we have f of x or f of t times delta t. So the distance is f of, since we're going the upper bound, we're going to go 1 times 1, then 2, and then 3. So we have 160 minus 9.8 times 1 times 1. 160 minus 9.8 times 2 times 1. And then 160 minus 9.8 times 3 times 1. One 60 minus 9.8. 160 minus 19.6. 160 minus 4, 30.4. It's 150.2, 140.4, and 120.6. No, 120, 130, 129.6. $50.2, 140.4, 129.6. So it's 4. Mhm. Well, carry the 1. It's 59, 60. 60. 59, 60. Yeah. So let's see. How close does the sum come to 435.9? So we have our lower bound was 4. No, this is our upper. We have 450.6, 420.2, and the actual was what was that? How close does it get to 435? So we have 450 minus 435.9. Then we have 435.9 minus 420. So this one gets 14.7 meters. The other one gets 15.7 meters. Well, let's see. What that's called, this is what's called an error magnitude. The true value minus the calculated value. That's just trouble. So now let's take another example of the rock going straight up. Displacement versus distance traveled. What is displacement? For example, displacement, if you have a tub of water and you put a bowling ball in there, the water gets displaced according to the volume of that ball. So displacement is simply a change, a value change based on some action. Distance traveled is just that, is just how far something goes from point A to point B. So the distance traveled is velocity times the and the total distance traveled is the sum of all those. That's the total distance traveled. Okay, now let me write that down. Displacement is the difference between the original and final position. Like I said, the example of the water. If you had a bucket of water, the water level's here. That's the original. I put the ball in there. The water level rises. The difference between the beginning and that one, that's displacement. So let's look at example 2. The velocity of a rock launched straight up is given by the velocity of is 160 minus 32 feet per second. Ah, notice this number now. Now it's 32. It used to be 9.8. What happened?
The last one.
Right, because of the units, right. Whenever you deal with metrics, the SAE system, we use 9.8. Whenever, the metric system. Whenever you use our system, the SAE in America, we use 32 feet per second. The rock was 256 feet above the ground, 2 seconds after explosion. Yeah, after exploding. And continued upward to a maximum height of 400 feet at 5 seconds. And it fell back down a distance of 144 feet. To reach a height of 256 feet. At 8 seconds. So what's the total distance traveled? It reaches total distance straight up is 400 feet, right? Then how far did it fall back down? Then it fell a distance of 144 feet before it got to that height level. So we add 400 and 144, we get what? Four hundred up plus 144 down equals 544 feet. You know, we could have used the distance, because remember, it all happened in certain time periods. So the distance was velocity times delta t. And the velocity formula was 160 minus 32 feet per second. The first number it gave us was at 2 seconds. It was 256 feet. Then it said after 5 seconds, it reached a maximum height of 400 feet. And after 8 seconds, it fell down 144 feet. So the question was, the total distance traveled after 8 seconds was what? 400 on the way up and 144 on the way down. So if we add them together, why do we add them together and not subtract them? Even though it's a negative 44% going down. Good question. Distance is an absolute value. The negative sign simply is a reference. Is it going up or is it going down? Is it going left or right? What's that? It's going down. So that's what it tells us. But the distance traveled is still 144 feet. Whether it's up or down, it doesn't matter. It's just we're looking for the total distance. The total distance that went up after 5 seconds, and then it fell down this many. So the total distance it traveled was 544 feet. So yeah, when we do distance formulas, we have to use that formula because again, distances are absolute values. All right, let's create the chart. So what we're going to do is we're going to create a chart that looks at the time and the velocity at that point. Because remember, our total distance, our total time estimate was from what to what? From 0 to 8 seconds before the trip was finished. So at 0, what's our velocity? What's our velocity? (160). At 1 second, what's our velocity? So it's 160 minus 32, 128. At 2 seconds, it's 160 minus 64. It's going to be 96. At 3 seconds, we have 160 minus 96, which gives us, let's see, 64, 160 minus 128. At 5 seconds, what do we get at 5 seconds? Because remember, what happened at 5 seconds is at the highest point. So the initial velocity and the height, the velocity of gravity have to be equal because it doesn't go any higher after that. So yeah, so that's where the equal. If you notice how these numbers are increasing by 32. What are these doing? Decreasing by 32 because that's what gravity is. So then when we have 6, 7, and 8, at 6, we got negative 32 from 0. Then we go negative 64 and then negative 96. But it's only 8 of them. That's the same as just leaving our graph with just one interval itself. So what we should do is here, let's cut these in half. So we're going to look at these intervals inside there. Because all of these original ones, our delta t was 1. So if we added up all those, we can add up all those. We can have 160 plus 128, blah, 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 times 1 times 1, because that's the interval. Now we look at all of these other ones. So at 1/2, what do we get at 1/2? So what number is halfway between 160 and 128. So it's 16, so it makes it 144. Because now these differences are half of 32, which is 16. So we're going to subtract 16 from each of these. 16 minus 128 is 112. 16 minus 112 minus 16 is 196. 196 minus 16 is 70. 170, no, it's 80. 180 minus 16 is 64, and so on and so forth. So the more intervals we put in there, the better we get. Here's what's going to happen. When we do our intervals, the total distance traveled is going to be 192. That's at using the half interval. So we have how many intervals? 16 intervals. Because we have from 0 to 1/2, to 1, to 3/2, to 2, to 5/2, to 3, and so on and so forth. If we keep on doing this, we'll have 16 intervals. Earlier, we simply had, here we have 16 intervals. Here we only have 8 intervals. What's going to happen is when we do that, we get much closer and we get a much better calculation. The last thing, we'll do this next time, is we're running out of time, is look at average values of continuous functions. For example, if we look at the sine function, we know it goes to 1. The period is from 0 pi to 2 pi. Let's look at this area here. What is this area under this curve? We'll do that next time. Or do you guys have a class right now? You have a class right now? At 10? All right. Go ahead. We'll finish this next time. Yes, Thursday it is. We never have classes on Friday.
I know. I have class on Friday, that's why.
You do?
Yeah,
Oh.
it's chemistry. I only have one class on Friday.
That's not good.
But
That sounds boring.
this one is,
There.
what day is the?
You too. I'll see you Thursday. Now, what are they doing out there? Do you know? Well, they had that loud volume. You know what's going on out there?
I don't know, I think it's like setting up something like that.
And it's gonna be pretty loud.
I think at the moment when I got there, I see a lot of stuff have been organized, a lot of stuff.
That's not gonna be good. And it's right here. You see how loud it is.
Yeah, because even outside, they're
So-
organized too, outside.
Well, it's a beautiful day.
So, yeah,
Have a good day, sir.
yeah.